Chapter 5, Section 5.2, Right Triangle Trigonometry. The objectives in this section include using right triangles to evaluate trigonometric functions, especially for special angles such as 30 degrees, 45 degrees, and 60 degrees, recognizing fundamental identities, such as the Pythagorean identities, using cofunctions and complements, and finally, evaluating trigonometric functions with a calculator. Let's see how the trigonometric functions are defined. There are 6 trigonometric functions. They are sine, cosine, tangent, cosecant, secant, and cotangent. They have abbreviations. Cotangent is the cot or COT, secant is SEC, cosecant is CSC, tangent is tan, TAN, cosine, COS, and sine is abbreviated SIN. These are the names of the trig functions. These are not functions, these are the abbreviations for those functions. In terms of a right triangle, here we have a right triangle with given angle located here, and we have this length labeled B, this length labeled A, and this length, which is the longest side of the triangle, always opposite the 90-degree angle, is the hypotenuse, and that is called length C. The 6 trig functions are defined as follows for right triangles. The sine of the angle is given to be the opposite length of the triangle divided by the length of the hypotenuse. So we say opposite over hypotenuse. The cosine of the angle is defined to be the adjacent length to the hypotenuse, adjacent over hypotenuse. And tangent is defined to be the opposite over the adjacent. So the trig functions are ratios of 2 sides of a right triangle, where the ratios are defined here for these 3 trig functions. Now, there are 6 trig functions, and I'll get to the other 3 in just a moment. It says here, in general, the trigonometric functions of the angle depend only on the size of the angle and not on the size of the triangle. So what that means is that if you have a triangle, right triangle, say here, and this is our angle theta, if you were to extend this triangle and make it larger, now this length is longer, this length is longer, and this length is longer. But notice that the angle is the same size. These are called similar triangles. So the values of the trig functions depend only on this angle and not on the particular size or the lengths of those sides, only on the angle. If you change the angle, then it changes the value of the trig function, and of course it changes the length of the sides. So the ratios are remaining fixed for a given angle theta. Okay, also note that if we put the angle theta in this position right here, then the opposite to this angle theta is this length, the adjacent side to this angle is this length, and the hypotenuse is always opposite the 90. So you have to always look to see where the angle theta is before you understand what means opposite, what means adjacent, and what means hypotenuse. Okay, the remaining 3 trig functions are defined here. These are reciprocals of the first 3 trig functions, so I'll try to put both on the same page here. So we have the cosecant, hypotenuse divided by the opposite, and that is the reciprocal of the sine, which is the the opposite over the hypotenuse. The secant is the hypotenuse divided by the adjacent. That is the reciprocal of the cosine function, which is the adjacent length over the hypotenuse. And the cotangent is adjacent divided by opposite, which is the reciprocal of the tangent, which is opposite over adjacent. That's why these 3 values here are reciprocals of these 3 values right here. Okay? And the same relationship holds for right triangle for these 3 trig functions, where it depends upon the size of the angle and not the size of the triangle. Okay, special angles. There are two special right triangles that we use in trigonometry. One is the 45, 45, 90 right triangle, and the lengths of the sides are as follows. The smallest integer length we can use here would be 1. If this is 1, this length must be 1 because these two angles are the same. So the side opposite those angles must also be same. By the Pythagorean theorem, this length squared plus this length squared equals this length squared. We can then figure out that the length of the hypotenuse is square root of 2. This is a very important triangle in trigonometry, and I suggest that you know it to be able to do trigonometry. Here's a second right triangle. This one is special. This is the 30, 60, 90 right triangle. Where the lengths of the sides of this triangle come from are to start with the triangle where it has all lengths equal. So this is called an isosceles, or equal angular triangle. And I will use 2 for the length of all three sides. Since the sum of the interior angles always add to 180, this will then be 60 for each one. So 60 times 3 is 180. Now what we'll do there is we'll bisect this angle right here. And there's a geometry theorem that says if you bisect the angle, then this forms the midpoint of this length here. So take away this part of the triangle and just use this part right here. We have a right triangle. We bisected the angle, so then this is 30. This angle is unchanged. It's 60. And since this is the angle bisector, the perpendicular bisector, this now forms a right triangle. Well, this length is still 2. Since this is the midpoint and the length was 2, that makes this 1. And by the Pythagorean theorem, we can then figure out the length of this side right here, and we would compute that to be square root of 3. So that's where that triangle is derived from. Now, 30 degrees is a pi over 6 angle. Remember, think of pi as 180, so 180 divided by 6 is 30. And 60 degrees is pi over 3. 180 divided by 3 is 60. So we can look at this as the 30, 60, 90 triangle, or the pi over 6, pi over 3, pi over 2 triangle. And it's a very good idea to know the lengths of the sides of this triangle. Be careful that it depends upon which angle you call 30 and which one you call 60. See, my diagram's not the scale here. If this is 30, then this is 1, this is 2, and this is root 3. However, there's nothing wrong with drawing the triangle so that this is the 30-degree angle and this is the 60-degree angle. The smallest length, 1, must go opposite the smallest angle, so 1 goes here. A hypotenuse is always the longest length, and the root 3 goes opposite the 60. That would go here. These two triangles here are exactly equivalent in every way. So you have to be careful to always check where the angle is located before you think about the length of the sides. Okay, let's take a look at example 1. Use the figure to find cosecant 45 degrees, secant 45 degrees, and cotangent 45 degrees. So based on the definitions of the right triangle, cosecant of the angle is the length of the hypotenuse divided by the length of the side opposite. Now here it doesn't matter which angle that you use because both of these are 45. The result will still be the same, which is root 2 divided by 1. The secant of 45 degrees is defined to be the hypotenuse divided by the adjacent. And again, it doesn't matter which angle you look at because the length of the sides opposite are the same. So you'll get root 2 either way. And the cotangent would be ratio of 1 since that involves the adjacent and the opposite length divided. So 1 divided by 1 is 1. Let's take a look at the 30, 60, 90 triangle. and obtain a few trig values from there. Example 2. Use a figure to find tangent of 60 degrees and tangent of 30 degrees. Okay, now see these angles are different, so you have to carefully look at where these angles are orientated on the paper. The 60-degree angle is located here at the base. The 30-degree angle is up here. So if we went tangent 60, you then have to put your eye here at 60 degrees. Look through that angle, and root 3 is the opposite length right there. That makes this the adjacent length, and of course, opposite the right angle is always the hypotenuse. So now it matters which angle you view through. View right through the angle for the opposite. Tangent of 60 is defined to be the opposite divided by the adjacent. So the opposite length is root 3, the adjacent is 1, root 3 divided by 1 is root 3. Tangent of 30, now we have to view through here. Look through the angle, and the opposite is this one, 1, and the adjacent is now root 3. So the tangent of 30 is 1 divided by root 3. Rationalize, multiply by root 3 divided by root 3 to obtain root 3 over 3. Okay, we could evaluate all 6 trig functions for 45 degrees, 30 degrees, and 60 degrees. I encourage you to do that, and you will see why these values for sine, cosine, and tangent are what they are shown here to be. If you want the values of the cosecant, since the cosecant's the reciprocal, we simply flip over each of these, reciprocate, we'll have to rationalize, and we can get the cosecant. If you wish to get the secant, secant and cosine are reciprocals, so you could reciprocate these and get the corresponding secant values, and the cotangent would be the reciprocal of these values here. But I encourage you to go to the triangle, go to the definitions, the right triangle definitions, and obtain the values of all 6 trig functions at each of these angles to get a little practice and a little confidence. Identities. Okay, as I noted, based on the right triangle definition, the sine and the cosecant are reciprocals. Now, if sine is a reciprocal of cosecant, then cosecant is a reciprocal of sine. It works both ways. Same is true for the cosine and the secant. They are reciprocals. And the tangent and the cotangent, they are reciprocals as well. Okay. The tangent and the cotangent, we have quotient identities. Quotient just means the division of 2 things. The tangent is also defined to be the sine divided by the cosine. And the reason why that is tangent, let's see, sine theta, let's get a right triangle here for reference, we need one. Let's put theta there, and we'll do A, and we'll do B, and we'll do C. Okay, so sine theta is opposite over hypotenuse, so that's B over C. Cosine of the angle is adjacent, so that's A over C. And if we take the sine and divide it by the cosine, then we get B over C all divided by A over C. Simplify that complex fraction. B over C times C over A. So the sine divided by the cosine, which here says tangent, C's divide out, and you get B over A, which makes sense because this is the opposite and this is the adjacent length of the side of the triangle for the angle theta. So it's consistent that it works in that way. And the cotangent here is in a similar fashion defined the same way. Okay, let's look at an example 3. Given the sine to be 2/3 and the cosine to be square root of 5 divided by 3, find the values of secant of the angle and cotangent of the angle. Okay, the secant is the reciprocal of the cosine, and we're going to use that definition because we have the cosine already here given. So simply take the reciprocal of the cosine function. So the reciprocal of root 5 divided by 3 will be 3 divided by root 5. We'll rationalize and simplify that to 3 root 5 divided by 5. That'll be the value of the secant. The cotangent, well, the cotangent you could define as the reciprocal of the tangent, but we need to be able to get the tangent first. So let's do that. So the tangent of the angle is the sine divided by the cosine. So that's 2/3 divided by root 5 over 3. Let's simplify that. 2/3 times 3 over root 5. So the tangent is 2 divided by root 5. That's the tangent of the angle. Therefore, the cotangent is the reciprocal, or root 5 divided by 2. So root 5 divided by 2 is right here. So it's slightly different from what is shown. There's more than one way always to get it done, but that's a good way to understand how to do that. Let's take a look at some fundamental identities that are used in trigonometry. The Pythagorean identities are very important, and they come up all the time in trigonometry. Sine squared plus cosine squared is 1. Now, note that when we write sine squared of the angle, we do not mean the sine of the angle squared. They are completely different things. When we write sine squared of angle, this is short for writing. Take the sine of the angle and then square the answer. These are very different things, but it's very easy to confuse them. So a different way to write the Pythagorean theorem is then the sine of the angle squared plus the cosine of the angle squared is always equal to 1. So 1 can be replaced by this expression and vice versa. Okay, we have two other Pythagorean identities here. I'll show you where one of them comes from. First, take your base relationship. Sine square plus cosine square is 1. From that, divide all terms by the cosine square. So we'll take this expression. Each term will divide by cosine square, and this one, and this one. Okay, since we did the same thing to all three terms, that's a valid math move. Now the sine divided by the cosine is the tangent. So sine squared divided by cosine square is tangent square. Cosine squared divided by cosine square is 1, and 1 divided by cosine is the secant. So 1 divided by the cosine square is the secant square. And that shows how to derive this Pythagorean identity right here. If you want to get this Pythagorean identity right here, start with the base relationship, and this time divide by sine square, sine square, sine square, all terms. Simplify, and you will end up with this identity right there. Complements. Trig functions and their relationships to complements. Two positive angles are called complements if their sum is 90. So 80 and 10, or 75 and 15, are complement angles. Any pair of trigonometric functions for which the trig function at the angle is the same as the trig function at its complement, in other words, based on the picture, if this is angle theta, then this is 90 minus theta. So these are complementary angles because these two here add to 90. 90 minus theta plus theta is 90. So these two add the 90, therefore these are complements. So a trig function from here and a trig function from here, if they're co-functions, then they will have the same value. So in other words, the sine and the cosine are co-functions. So if you were to take the sine of this angle and its co-function cosine from this angle, you will end up with the same result. So for instance, the sine of angle theta, based on this picture right here, that would be A opposite over hypotenuse A over C. Whereas if you take the cosine of its complement, 90 minus theta, now you're looking through the triangle here, through this angle. Cosine is adjacent over hypotenuse, so that's A over C. And they're the same thing. So that's what it's saying here. That motivates the following co-function identities. The values of trigonometric functions of the angle theta is equal to the co-function of the complement of theta. So listen to the names of the trig functions, the sine and the cosine, the tangent and the cotangent, the secant and the cosecant. Now you understand more about why they're defined the way they are, why their names are what they are. And of course, if one is defined at theta, the other one at 90 minus theta, if they're co-functions, trigonometric co-functions, then they are equal. Okay. So for instance, for example, suppose you got the sine of 46 degrees. Then the sine of 46 would be equal to its co-function, the cosine, of 90 minus that angle. This is the angle theta, this is 90 minus theta. So the sine of 46 is the same thing as the cosine of 44. You could verify that one on the calculator if you wish. The cotangent of pi over 12, the cotangent is the co-function to the tangent. So tangent and cotangent are co-functions. So the cotangent of theta is equal to the tangent of 90, see here we're in radians, so you have to use pi over 2, 90 minus theta. Find common denominator, and we would get 5 pi divided by 12. So the cotangent of pi over 12 is exactly the same as the tangent of 5 pi over 12. Okay. Speaking of calculator, let's take a look at that just briefly. Most calculators have buttons that are labeled sin, cos, tan, sine function, cosine function, and tan function. But you have to look at the problem at hand to make sure whether the problem is in degrees or radians and set the mode on your calculator to be in the desired measurement system. Most trig functions buttons on the calculator work by first saying what trig function you want and then putting in the angle. So most of you would hit the sine button and then 30 for sine 30 degrees and then hit enter. Some calculators work backwards where you have to enter the angle first and then press the trig function that you want, sine, to get the answer. But the TI calculator system uses the trig function name first and then the angle second. Example 4. Set the calculator to degree mode since we're working in degrees and hit the sine button and then 72.8 and then enter, and you will see the value on the screen is approximately 0.9553. The cosecant of 1.5. Okay, how do you know if this is degrees or radians? If it's degrees, you'll see the degree symbol there. We don't see it here, therefore this is in radians. So set the calculator to radian mode. Now, you don't have a cosecant button on the calculator. So what you can do is, since the cosecant is the reciprocal of the sine, if you find the sine of 1.5, and you get your answer, and then the cosecant of 1.5 is 1 over the sine, so it's 1 divided by that answer. They are reciprocal functions. Okay? So find the value of the sine, and then reciprocate that, and you'll have the value for the cosecant. Sure, I got that on the screen there. Find the sine of 1.5 on the calculator, and then to get the cosecant, take 1 over that answer. Take the reciprocal of that answer. Okay, that's the conclusion of section 5.2.